Hello, everyone. My name is Dr. Gavala, and today I will be talking to you about EE220, which is basic circuits at most universities. And what we're going to talk about in this course is we're going to talk about circuit terminology. Then we're going to dive into resistive circuits. And then we're going to talk about analysis techniques. And then next, we're going to talk about op amps or operational amplifiers. And then next, we're going to dive into RC and RL first order circuits, where R and the C stands for resistor capacitor, and the R and the L here stands for resistor inductor. And next, we're going to talk about RLC circuits. And then we're going to dive into AC analysis, which stands for alternating current analysis. And then we're going to dive into AC power. And then lastly, we're going to wrap everything up with frequency response. Frequency response of circuits and filters. So, who is this course geared to? This course is geared to sophomores and juniors in electrical and or computer engineering. Some prerequisites. And essentially the prerequisites which you should expect to know for this course are chemistry, physics, and this is in most universities 100 level or sometimes a 200 level chemistry course. Physics similarly 100 level or 200 level physics course, and math 100 level or 200 level course. Specifically, calculus is required, and this is calculus 1, 2, and 3 is required. So let's dive right in, and let's talk about critical units and very important units. Very important units, dimensions, and notations that will be used throughout your entire electrical engineering coursework. So I'll write out electrical here. I'll write out the name, and I'll write out the unit and this other symbol. So to begin, we have current, and this is called amperes, and the units are ampere, and the unit is A. And then voltage, or this can also be called amps. The name is volt, and the unit is V. We have resistance. The name is ohm, and the unit is this horseshoe type of looking symbol. For the next component, we have capacitance. The name is farad, and the unit is F. For inductance, the name is Henry, and the unit is H. And then next for power, the name is Watt, and the unit is W. And lastly, for frequency, the name is Henry. The name is Hertz, and the unit is Hz. In terms of some key circuit representations, circuit representation. If you have a DC source, such as a battery, this is how it's represented on a circuit. And the value of the source is normally depicted somewhere next to the symbol. Additionally, if you have an AC source, so this is a 6 volt, this one is a 12 volt AC source, and with AC you need to give the frequency, where DC is direct current and AC is alternating current. The symbol for that looks like this. And again, you have to put the value somewhere next to the symbol. Next symbol is a fixed value resistor, which looks something like this. A regular variable resistor, as we will see in the future, looks like a regular resistor, but with a line slash through it with an arrow. The symbol for a capacitor is depicted by a line with kind of like a T that's facing to the left and a T that's facing to the right. For an inductor, For an inductor, we have a line that looks like that. And if we wanted to depict a transistor, which will be discussed later, or let's say an operational amplifier, an op amp, and then we'll talk about the picture for a transistor. And we'll also draw the symbol for a transistor. And those symbols for an op amp, first off, looks like this. And for a transistor, looks like that. This. Next, we want to discuss an example. First we want to define what are considered nodes. Nodes in wiring. So a node is an electric conductor, conductors, or wire that connects two or more circuit elements. Where we have something called an ordinary node. Ordinary node. And this only has two elements. And this is extremely important when you're doing circuit analysis. And you also have what we consider an extraordinary node. Which has three or more elements. Let's start off with an example to see this in action. If we're given a circuit diagram that has all of our components that were named earlier, the resistor, the capacitor, and then I'm going to go ahead and draw an op amp here. And this may look a little scary to begin, but at the end of this course, or the end of this series, you will know exactly how to analyze a circuit like this without even drawing it out or thinking about it. You would simply ask for values of the resistors and the inductors, capacitors, and you would be able to tell what the V out and the V in is. So I want to make note of this. So first off, this is a DC. So if we want to just go around our circuit here and name components, this is a DC source with, we call this V2, where V2 is equals to 6 volts. This is an AC source. An AC is a sinusoidal signal, where this is time and this is the voltage V. So in this case, this is V1 of t. So in our situation, this is an AC source. This is an AC source with V1 of t equating to 12 cosine 327t of V. And this is this value for V1 of t is a sinusoidal that looks something like that. Next, this is an operational amplifier. Operational amplifier. And in a circuit like this, we need to define what we call ground. And ground normally is on the bottom right here. And we'll define what ground is. A lot of students, a lot of individuals believe ground is always where V is equals to 0, but we'll see later on that this is not always the case. Next, we want to identify our ordinary nodes and our extraordinary nodes. So again, the ordinary node is where only 2 elements meet, and the extraordinary node is where 3 or more elements meet. So in circuit design, we really only care or really only identify our extraordinary nodes, but in this case, I will do both. So beginning with the extraordinary nodes, N1 is right here, N2 is here, N3 is right here, and that will be all. So we have, again, a lot of ordinary nodes. As a result, we don't name them specifically, but for the sake of introduction, we will name them in this lecture. So this here is a ordinary node. Let's say O1. This is also an ordinary node, O2 right here, O3 right here, O4 here, O5. And this is also an ordinary node. Oh, sorry, this is an extraordinary node. So this would be N, we said N3, N4. This would be N4. Simply because this component connects to it, this component, this component. So that's 3 or more. So and essentially this entire line is considered one node. This is the same node. And we consider that an extraordinary node since it connects 3 plus components. So I hope this concept of ordinary nodes and extraordinary nodes makes sense. Briefly, another symbols for ground. So ground symbols could be this, or it could be this. It just depends on which one you prefer to do. Now let's identify some key important words in electrical engineering, and that is specifically series. Something is in series or something is in parallel. And this is used all over electrical engineering, where if you have a circuit that looks like this, this is V1, V2, minus, plus, plus, minus, plus, minus, and you have a current, say I, flowing through this circuit. Again, this is your V source, or this could be your V battery. We can say that I1, so the current through here, I1, and the current through here, I2, I1 is equals to I2. And V1 is not equals to V2. And this goes back to that same concept of ordinary nodes and extraordinary nodes. As you can see, we have an ordinary node right here because it's only two components. Where when you have an ordinary node, those components share a current, but they don't share a voltage. Now in parallel, if we have a similar situation, V1 plus minus, V2 plus minus, minus plus. Again, this is considered Vs, or your V battery, V bat. The I is leaving from the source. Normally call this IS, so this could be IS. And the current flowing through here is I1, and the current flowing through here is I2. And the idea is now, in an extraordinary node situation, located right here, the current, the voltages, V1 is equals to V2, and the currents I1 is not equal to I2. So as we see here, we have, keep in mind that all we can say is that for this case, located here, I1 is equals to I2, and V1 is not equals to V2. But in this case, we can say that I1 is not equals to I2, but we cannot necessarily say that V1 is not equals to I2. And the reason why is because, as we will see, this can be an extraordinary node, but we can insert a resistor here. And we can insert a resistor here. And in this situation, I1 will not equal, or V1 will not equal to V2. And I1 will not equal to I2. So we should be careful when dealing with extraordinary nodes. But what can be said is that when we have an ordinary node, as depicted in here, right here, is that if two components share an ordinary node, it definitely has they definitely have the same currents. Next, we'll give an example, and this will be the end of this session or this lecture. And the example that we want to give, again, looks like this. This example will allow you to be able to get used to circuit drawings and how they look. And by the end of the course or the lectures, like I said earlier, these will become second nature. Where if we give this as 12 volts, 5 volts, 1 volt, again, maybe ask yourself, what does this represent? Is this an AC source or a DC source? Now, we're given resistor values of 1 ohms, 8 ohms, 4 ohms, 6 ohms, and we're given circuits, currents, I1, this is I2, this is I4, this is I3, and this is I5. If you are asked the question, which current is the same as I2, I want you to pause the video and answer that in your paper. And I'll answer it now. Essentially, as we can see here, I2 shares the same path as I4. So we have a ordinary node here, and we have an ordinary node here. As a result of that, I2 shares the same path with I4. So we could say I2 is equals to I4. Next question will be, under what circumstance would I1 equal I2? So actually in this situation here, we only have an ordinary node right here, which connects I2 to I3, or I2 to I4. So in our second example, under what circumstance would I1 equal I2? So essentially this is I1 coming in here in this direction. And the question is, if I have I1 coming here, what will allow that the current coming in here must equal the current coming out of here? What must be the case? So maybe pause the video again and see if you can answer that. And the case that this happens is only if I3 plus I5 is equals to 0. So that means that if no current flows through here and no current flows through here, all my current will be flowing through here, causing I1 to equal to I2. Now, in terms of pictorially or in drawing, I want to show you what current does so you can relate it to your daily lives. If you're leaving your home and you're driving to work, and there are two paths, one could be the highway and one could be the side streets. Essentially, if the highway is empty, you will go through the path of least resistance. Let's say there's traffic, there's cars on this side streets. You will go and you will take the highway to take you to work. And if the number of cars on the highway were the same, so let's do 4 cars and 4 cars here, then your choice of going to work would be split. You might go to work some days on the highway, and then some days you might go to work on the streets because it's the same time. And this concept of you going to work is similar to how electrons flow through a wire, where the amount of cars in our situation, the amount of cars on the highway, let me say cars on highway, is equivalent to the resistance or the resistor value in a wire. And the higher the resistance, the less chances an electron will flow through that resistor. So simply put, in a schematic, if you have a voltage source, this is the home in terms of analogies, and you have a 10K ohm resistor and a 1 ohm resistor connected, and this would be like your load RL. So this is your work. So this is your RL. Your RL is your work. The electrons would choose to flow through the 1 ohm resistor, or in this case, the side streets, same as a human would do. So in this movement of electrons and through wires to go to a load is essentially all we do, is a major part of electrical engineering. I don't want to say it's all we do, but it's a very, very major part of electrical engineering. We just move electrons from one end of a spectrum or a point to another end. And when it gets to this point, RL, it does work that we want, and then we send it back home to ground. All right. So to continue our example, we want to ask the question, this could be C, which elements or combination of elements in the circuit are connected in series and which are connected in parallel. Now, again, pause the video and see if you can work that out. Now, We'll define that two or more elements, and this is what I explained earlier, but now I'm just going to write it out for less ambiguity as we move forward. Two or more elements are connected electrically two or more elements that are connected electrically two or more elements are connected electrically in series if the same current flows through them. Flows through them. Flows through all of them. And let me use a different color here. And they are connected in parallel if they share the same nodes. All right, so we're going to rewrite our circuit and we're going to break it down into a combination of series and combinations of parallel components. So from our previous example, and I'll write it out without writing out the values of the resistors or the values of the supplies, the voltages, just so we can see it. So we can redraw this to look something a little bit easier with the eyes, because this might look a little confusing. This can look a little confusing. These delta configurations is what we call them, because it looks like a delta. So we know that this is a node, and we want all the components connected to this node to be in place. So we could just write that node here and expand it as such. And we could expand the rest of our circuit in this manner. Now, without going into too much detail, but I hope we see how we go from here to here. So just to kind of picture it out, this node here is expanded to this line here. So this is the same node. This node here is expanded here. And this node here is expanded here. So maybe pause the video and make sure you understand how we got from here to here. Next, we'll realize our in-series connections and our parallel connections. We first say that this here can be considered in series, again, because they share a ordinary node. As a result, they share the same currents. And from our definition, two or more elements are connected electrically in series if the same current flows through them all. So in this situation here, we get the same current flow because this is just an ordinary node. And because of that, we can shrink this. We can call this C1, and we could shrink this down to look something like this, where this is C1. This is that resistor right here. And the rest of our circuit follows. And for simplicity, we can do the same thing to this side of the schematic. We could just say this, again, so for the same rule of our ordinary node, this is C2 and it's connected in series. So maybe I should write series and I should write series. And this all comes together right here, C2. And then lastly, and then next, we can consider elements in parallel. So we define elements in parallel being elements are connected electrically in parallel if the same, if they are connected, if they share the same node, same nodes, right? So if we come down to our circuit, this is a common node, N1. This is a common node, N2. So this is the same node as here. And this is a common node, N3. And this is a common node, N4. So C1 and this resistor share a value, so they're connected in parallel. So we can consider this P1, and we can consider this P2. Again, the concept of series and parallel are extremely important for the development of this class. So we can then shrink our circuit even more, and we could say that P1, P2, and now we just have our plus, minus. And now we again know that these three components share the same current. Again, you can think about it as there's only ordinary nodes in between them. So there's an ordinary node here, here, and here. So they share the same current, or per our definition, they have the same current flowing through them, through all of them. So we can then now say that this is an in-series combination. So we can actually just write our schematic just for simplicity as if we say that this is S1 in series 1, we could generalize our schematic to be S1 is in series with plus minus our voltage source. So this is how we can kind of reduce, or we can analyze this complex delta circuit and simplify it into something like this using our knowledge of series and parallel. And we'll end there, but in the next lecture, we're going to talk about electric charge, and currents. And it's a very important lecture, always asked in interviews. And also don't forget to like, subscribe, share the video, and I will see you in the next one.